Hello world. Yes, these are some of the most famous and oft-quoted words in computer science. This is Dr. Keith Schubert, and this is kind of the introductory video for my offline notes for what's 535, essentially an overview of scientific computing, or if you happen to like mathematics, the traditional term for mathematics is called numerical analysis. Now, what we're really concerned with as we're going through in these problems is the idea of what it's all about. We're trying to solve physics, other scientific problems, engineering problems, problems that have essentially continuous values, and we're trying to solve them on a computer, which cannot solve problems with continuous values. We are stuck with discrete values. So we're kind of like doing an algorithms course, as you might have, at Cal State San Bernardino. This is 431, algorithm analysis. In that class, you deal with integer algorithms, and you solve a lot of interesting ones and look at complexity, and these are things that matter to us as well. But we're also now concerned with the second problem that creeps in. In ours, we can't even represent our data or even calculate exactly what's going on. So, we have to consider the effects of these approximations, and we want to be able to simulate some type of natural phenomena. So, these type of areas we can use in prototyping, we can use in lots of things. But these are of crucial values to us as it goes on, and particularly for those of you who are computer engineers, or if you're in games, things of this sort, it becomes very important to you to be able to get a good accurate result quickly. Now, there are ways we can do symbolic computation, but there are some problems that cannot be solved symbolically, and in many cases when you can solve them symbolically, it is extremely difficult to do. So we want to be able to tackle these. Now, in order to do this, we have to consider a basic issue that comes on. And the first part of this is, can I actually really solve this? Right? So in order to address that, we want to talk about well-posed versus ill-posed problems. So it's probably helpful if I come in here and now separate these up. This is kind of our first issue, well-posed or ill-posed. Which of these is it? Now, we really want these. We want well-posed problems. But what is a well-posed problem? Well, well-posed problem, we want to be able to have a solution that first off exists. It's kind of hard to find an answer to something if that answer isn't really there. If you're looking around and it's not there, it's not a good situation to be in. Now, the second thing that we would like about our solution is we would like our solution to be unique. Right? So, a unique thing, like everybody always talks about wanting to be unique. We all want to be special and whatnot. Now, this is not just a feel-good situation. This is a practical issue for us. If there are infinitely many solutions that all work, how do you know which one is the right one to use? Or if there is no particular right one to use, get into issues of what does it matter, how do I, pick ones that are all equally good. These become issues to us. Now, there's another one that comes up to us, which is we want it to depend continuously on our data that's coming in. And this becomes particularly important for us when we're solving a lot of different problems. There's going to be continuation methods in that. Essentially, we want something that's fairly smooth as it goes. Now, there are problems that are out there that you don't want your data to depend, or your solution to depend continuously on the data, because it would be too easy for somebody to just tweak it a little and see how it goes. Those ones, when they depend really continuously on the data, would be a disadvantage. So for instance, if I were doing cryptography, I would like something that jumps around a lot, that makes it very difficult for somebody to follow. I wouldn't want it to depend continuously on the data in that situation. But that is not the type of problem we are going to be tackling in this, though it is a very interesting problem. So now note, by putting this requirement in here, I haven't removed that it could still change fairly quickly. We're going to talk about that. That's our next issue, which is, sensitive or not sensitive. So it's kind of our second question that comes up. Is it sensitive? And what we want is something that, ideally is not going to be sensitive to it, and we'll show how we talk about this. This is something I'd like to get to in the end of this little recording we're doing here, which is the idea of a condition number, which will be kind of how we're going to deal with this for our first cut area. But what we mean by sensitive has to do with, depending on what my input is. All right, so let's say I've got, from wherever my inputs can come from, I get some piece of data x1, and I have a function that I'm going to calculate things off, and it maps it to a solution in a solution set, which is some y1. If I took something fairly close by, let's say x is right there, if I took something fairly close by, some x2, if it causes a wildly different answer over here, y2, then we would say, that it's a fairly sensitive problem. Right? So what we're looking for is, how does this change versus this? And if this change is large versus that, then we're going to call that very sensitive. So we'll come back to this in a little bit. Now conversely, if on the other hand, there's not a lot of change for a given input change, then we're going to call that insensitive. So that's now what we're going to get into as issues. Now, to get to that area of being able to analyze this, we need to be able to look at some of the areas of why might this occur and where do these issues come up. So amongst those, we're now going to start taking a look at some of those issues. We're going to deal with issues on, how do we handle problems? Now, and why do these sensitivity issues become important to us and creep in and things of this sort. So let's say we've got a problem. Let's say, I've been hired by somebody. Let's take a classic old one. Somebody's, got their cannons over here and they want to shoot somebody over here. Right? There's a lot of numerical analysis start on this type of a problem. Now, depending on how far this distance is, right, we've got the ability, shoots, I can change my angle. So based on what my angle is and how much charge I put in there will tell me how far my cannonball is going to travel. So we say, okay, great, we can approximate this now by taking an angle theta, right, and we have some type of, say, like an initial velocity that is put on it, and we want to find out what is the range that this can go on. Now, okay, how do we actually calculate this? Well, this is like your typical problem you get in your first course in freshman physics as you go through. When you look at that first course in freshman physics, they make certain assumptions. Like, the real problem is actually quite nasty, because everybody says, oh yeah, it's pretty simple, we just take, gravity, and we just assume, that your x double dot going in this one, that we just say, ignore it, but in here, y double dot is g, and, solve the whole thing, and see where we go. But in reality, you've got atmosphere, so you've got drag coefficients that go on based on your velocity, and there's wind, and there's humidity and temperature differences, and there's terrain height differences, and all kinds of funny things. And wind isn't a constant force, it's got all kinds of things described by partial differential equations and things of that sort. Now, if our approximation down to that simple model where we're just considering g as our effective force on that cannonball going once it's launched in the atmosphere, If that simplified model didn't work pretty well, we wouldn't use it. So our approximation has to be useful in this sense, and it turns out this is overall fairly useful, and then there are improvements that you can make on it. Now, the reason why I bring this up is we want to be able to find improvements that we can do inside of our problem set. And what we would like to be able to find in these areas is how to make the problem simpler. Right? So we'd like to be able to do things like take, infinite dimensional problems, and we'd like it to go finite. Right? We'd like to be able to do things like, nonlinear and go to linear, if we could. In general, we're doing complicated to simple, right? We can, a classic one we often do in engineering is we try to convert, calculus problems into algebra problems. That goes on, right? Differential to algebraic, all these kinds of lovely things that go on, and we have a bunch of techniques that help us to accomplish those. So we'd like to be able to simplify our problems, but the second we simplify them, we're only an approximation. Right? It's no longer the actual original, so kind of coming back to our sensitivity issue that comes in here, we have a second issue that's going to creep up here, that I don't actually have the true f, I actually have an f prime, which is an approximation. And that's going to become one of our big issues that'll come in here is I do not have reality. I have something that kind of approximates reality. Now, we want to look at some other things. There's also sources of errors beyond just my model is an approximation. I can have some other sources of errors. Right? So modeling is one area. I can take measurements. Right? I want to find out the length of something, and I got whatever, some object. I want to know how big is whatever this thing is, and I take my ruler up. And my ruler, is only, I only have so many tick marks here, and I only see it so well, and that can have all kinds of funny shapes, and maybe this has some 3D things, so I can't get exactly up against the line, and I can put a pencil on the end and mark it, but then I got the width of the pencil in it. There's lots of stuff that can go on. I can do fancy stuff like, take a photograph of that thing and try to measure it, but, depending on how I tilt the camera, it can actually alter things. You might not be able to notice it here, but you see my lovely little example here that's going on. This probably looks fairly straight to you, but it's actually not. If I were to actually show you in the thing, what you've got, my piece of paper is here on the desk, and I actually have marked out, it's a shape like this, it's not even, because my camera is off center, so my arm can come in easier here to be able to write. I have to stick the camera over there, so I have to tilt the camera at a weird spot. And it's back a bit, because I can't get right over the paper, and so I get this kind of funny window, which is actually why I have this in here. I've got these dark markings on the sides, which tell me where it's at. And I started drawing what was a shape, and then I looked in the window and went, ooh, no, it goes higher up, no, it goes higher up. Oh, wait, it actually goes all the way out to the side here. I had started drawing one on the far side of paper and discovered it's over a tiny little bit. So, there's approximations, and our measurements are not good, and things of this sort. Our things could also be related to previous computations. I might actually be starting off with data that's related to the volume. And so maybe when I calculated the volume from these, I had errors that had to do with modeling and the rest. Now, when I actually go in, so these are our sources of errors, right? We've got modeling, we've got our measurements, right? We've got areas of those measurements being, used through a model and then calculated again, so we kind of do this recursively. When we're actually doing those computations, I don't have infinite precision within my machine, so I have to round them, and I have to, truncate some calculations. So I've got rounding, and I've got truncation. And in some cases, like with multiplication, your numbers get bigger, so the larger the number, the worse things get. All these things start adding on to themselves, and pretty soon I can start rapidly losing a value. I can end up with big problems in here. So, we want to be able to keep this to a decent value and to get a decent error, decently close, a low amount of error by the time this whole thing's done. Now I've introduced the magic E word, right? Error. This is going to be one of our underlying ideas. I don't want to spend too much time on it because I think, sometimes people get too nitty-gritty on measuring error all the time. It's something you have to understand, but not necessarily something you're going to spend all of your time worrying about. So we've got two different types of error we classically deal with in big categories, what is called absolute error and relative error. So absolute error means if I know whatever is the approximate value. Now we usually say the approximate value by sticking a hat over it. So if the real value is x, its approximation is x hat. Sometimes that means approximation, sometimes it means measurement, but same idea as far as we're concerned. So if I want the absolute error, we'll just call it AE, that's this difference. Now if I want the relative error, then what I want is my x hat minus x over x. So that's how we're going to define our absolute and relative errors. So, now you might wonder, why do I do each one of these? This is called absolute because it's, because this one is relative. It's relative to the size of x. And this one does not matter on how big the numbers are. So a big number or a small number, you don't know what x is or x hat, this is absolute. Well, here's the reason why this one is usually the one we're more concerned with down here, the relative error, is because if you think about it, let's say I told you my error was 1 meter, right? So I have an error of 1 meter. Now, if most people here, I have an error of a meter, right? So if you like English units, a little bit over 3 feet, you might think, wow, that's horrible. Well, horrible compared to what? What if I told you that this was on, landing Curiosity on Mars? Being within a meter in that case, you go, wow, that's amazingly good. Now if I told you that, that is how close I got by, dropping a pen into a trash can and I'm standing right above it, but I only got within a meter of it, you'd be wondering, how could I be so inept as it goes, right? So, your error matters on what the size values that you're dealing here, right? So if what I was aiming for was something, just mere centimeters away, but I ended up being something that was, over a meter, right? Absolute error doesn't tell you much. But when I do this and I get that divided by that small size of a few centimeters, then you start to realize, oh, the factor-wise, I was a factor of hundreds off. And you go, oh, that's not so great. Right? But if you discover that, I'm doing something like going to Mars and I'm dealing with millions of miles here or millions of kilometers, and then all of a sudden, I'm within 1, you're like, wow, that's extremely good once I divide out by how far I was going, the millions of miles. So relative error in this sense I think is a lot more useful. Absolute error is used in calculating it, so you can notice that your relative error can be expressed as your absolute error divided by x. So that's kind of a helpful thing. Absolute error is a nice quick first way to get things. But again, I think there's a little bit of advantage in actually using the relative error because it does give us a sense of how well done this thing is. Now, if what we're doing is dealing with a computational error on something, as I continue to destroy paper at a alarming rate. Sorry to everybody who is sensitive to such things, but I've tried using whiteboards and it really doesn't work very well here. Maybe I can get a good whiteboard later on. I'll look around for one. So let's start off with our problem that I had before, which was I have some x, and I'm mapping by some function to some y. Now, as I'm going on here, I want to find out what is the total amount of error in whatever I calculate. Well, the reality is I don't have x1, I really have x1 hat. And I don't really have f, I have f hat. I have an approximation of the function. And so I end up with this new spot, which is really kind of almost a double hat here, right? It's a double estimate. It's based on two different things going on. So our total error really is the f hat, x hat, and I'm now going to take that and subtract what I should have ideally gotten. That is really my total error in an absolute error sense. Now, this can be broken up into two little portions to take a look at it. And I often mention to people there's only two tricks in mathematics: multiply by 1 and add 0. It's a little bit of an exaggeration, but if you start thinking about it, it covers an awful lot of cases. The trick is knowing what is the right 0 to add or the right 1 to multiply by. In this case, I'm going to add nothing. But the correct nothing that I want to add, I want to get some sense of, the bound of the error by doing computation. How does this computation relate just to if I had used the correct one? Well, to take a look at the computational effect, I need to have it compared with the same start but different functions. So this will allow me to assess how well f does. Now, this does not exist in the original statement, so I've got to get rid of it. And I get rid of it by both adding and subtracting it. So now this right here in the middle is 0. And then so I still have x1 left over. Now, as I mentioned, maybe I should do this in a different color here. This part right here is saying computationally, what happens, what's the error due to switching my function? This is kind of your computation error as it goes on. And I'll do another color for this side over here. This one, it's the exact same starting function, but it works on the different data. So this inside, if I was just doing x hat 1 minus x1, that would be the data error. And this is, kind of what happens if I had started from here and I had used actual f. Right? And so that one is telling me how the data error was propagated. I'll put prop in there for propagated just to keep it straight. Oh, that's a little bit out of screen, so we'll fix that one up here. So that's my propagated data error here, which is just telling you, again, an idea of, if I had started at that spot, and how big would the error have been if I had used the right value. And that is kind of my y1 hat. That's what this one is measuring. And then this one is saying how far is that, based on just you kind of used a different function. So it separates it out into its two pieces, which we're going to be concerned with. It's kind of, how bad was your data measurement, and this is kind of giving you some idea of how bad your algorithm is doing that's doing the approximation. And that's kind of our classic split up of these two. Now, we want to get these and be able to look at some ideas of what's called forward and backward error. This will be, I promise, my last dualism here. Of these errors that we often deal with here, we want to go forward and back. Now, I messed up that sheet all over the place, so I'm going to draw again. I'm not going to group them this time. I'm just going to kind of give this classic little thing. Here's our x1 going to y1. I'm not even, well, I guess we can put f on it. Alright, so here's my map of the points. Now, under this, I could consider, what if I took the true data and mapped it through an approximate function? And I would get a single, right, one of our kind of single y hat things. Now there's a second way of looking at this, which is the, what if I had the problem of x1 and the x1 hat. Now x1 hat could go to some other point, but I could, x1 hat is just something nearby. Right? So since it's somewhere nearby, I could consider the problem of, right, from ours, what if I had this for f? Now is it guaranteed this is? No. What we do is we say, hey look, I know what this is, and I know what f is, so I pick x1 hat such that if I did f inverse of y1 hat, that would give me x hat 1. And if you want to continue it one further, you could then end up with our f hat on this one, and you would end up with the y1 double hat. But we're not going to worry about this at the moment. We're just going to look at this upper part of the picture. Now, what we do on this side here, if I'm just considering same original data going through my algorithm, right, either the true algorithm or my approximation, this gives me what we call our forward error. Right, it's forward error because both functions, it's mapping from my data to my outputs, inputs to outputs. We consider that kind of forward as our data is flowing. So that's why it's called forward error, because we're just saying what's the error in the outputs. Right? Based on the same input, just comparing the two methods. Now, the one that strikes people as weird is what's called backward error. Backward error is the difference between x1 and x hat 1. This is our backward. And it's backwards because you normally think, hey, what's the difference on the outputs, not what's the difference on the inputs. But that's actually what we worry about for the backward error, is what's the difference on the inputs. You might say, well, how does that tell me anything about what's going on in the outputs? It tells you on the outputs because I made this assumption right here. I made the assumption that x1 hat is actually f inverse for y hat. And y1 hat is the f hat. So it actually accounts for it. What you really have is your x hat 1 is equal to f inverse of f hat of your x1. So that gives you a nice closed form solution for what it is. It's always that because we make the assumption. I've made the assumption that what I want to do is set x1 hat through f to be y1 hat and x1 through f hat to be y1. You make that choice. It is a definition. The second I make that choice that I'm going to force it to always be that, I can now write this equation and I can calculate the backward error. And the backward error is then comparing the difference from this to the original x, which really is looking at how do I map through the function. I get the f hat here, I get the f here, and it's in composition, and what would that be different from how this originally went? Now, if this was f, right, f inverse of f should just go back to essentially doing an identity mapping, so therefore x1 minus x1 would just give me 0, so I should have no error if I was doing the actual system. But since this is an approximation, this will give me something close by to where x1 mapped, and then the inverse will take me back, but it can't take me back to the original spot because I wasn't at the actual output areas. Now, you might go, wow, that's kind of a convoluted definition. The reason why we do this one is it turns out for a lot of algorithm proofs, this one's easy to calculate, and it turns out this one's pain in the butt. And it really just comes down to, we often can kind of group and aggregate stuff and therefore talk about general behaviors with this, Whereas on here, there's often a lot of things that have to propagate through. And the best way I can kind of give you a thing on that one is, imagine I was just doing a matrix multiplication. If I wanted to find out the forward errors on it, I'd have to do every matrix multiplication. The backward errors, when I'm doing it, I can actually just do it kind of grouped, worst case scenario, doing on the inverse, and I can get a bound on it. And it turns out it's easier to do the bounds here than it is the other way. And so that's really why it's there, is because it's just helpful to us. It's simple, and we're really all about making our lives as simple as possible. Now what we'd like to do is calculate a couple quick examples of how do I actually do this. So kind of keep this picture in your mind, and keep that definition in your mind if you want as well. And what we'll do is we'll just take a look at some kind of classic ones. Let me go back to my original kind of mapping down here. I've got a tall enough stack. I want to make sure I'm staying within my window. It's part of the reason why I wanted this dark enough that it can bleed through so I could follow. Okay, now let's consider the problem of f of x is, let's say for instance, cosine of x. A classic little simple trig thing. Now cosine of x is fairly difficult to calculate because it's, you know, a transcendental function, all this kinds of lovely stuff. So what we're going to do is we're going to approximate it by its Taylor series. In Taylor series, you take a certain number of terms. We're just going to take the first two terms. And so this is the first two terms of the Taylor series. And so that's going to be somewhat close to cosine, but it won't be exact. And the further out you go, the worse it's going to get. So first we want to consider what the forward error is. So in order to do forward error, I have to be able to look at what's going on here. The forward error is the error in the outputs. So that's kind of the change in y values. And so the change of y values, that's y hat minus y. Right? What your estimate is minus your original. Remember, we always do you know, your estimate minus original. So that is, in our case, the f hat of x minus the f of x. And our f hat is 1 minus x squared over 2. And our f of x is cosine of x. So that is the expression for my forward error. The expression for my backward error that is kind of our delta x values. And remember, our idea of being able to get a delta x was, this is x hat minus x, and our delta x was just the f inverse of f hat of our x, and then we're going to subtract x from it. And in our case, f inverse is arc cosine. I'm kind of running a little bit out of room according to this, so I'm going to go down here. A cos, arc cosine of 1 minus x squared over 2 minus x. So that gives me my expression for what is the forward and backward error. Now we can stick some numeric values in. Really, once I've got these equations, now when I ask you to calculate something on this, this is just a plug and chug issue, right? And so just as kind of an example of that, let's take a look at the forward error. Alright, so I'll just put FE, and we'll assume that x equals 1. And I'm assuming x equals 1 because it's fairly straightforward for me to calculate stuff. So to do that, I need to have, and it's kind of nicer if I have my numbers calculated out, but we can stick them in here and go. Forward error, in our case, we have 1 minus 1 squared over 2, so that's 1. So 1 minus a half, so I have a half, minus cosine of 1. Now, cosine of 1 is pretty darn close. I'll just put cosine 1 here. but that's approximately equal to 0.5 minus, and it's 0.54 and some change, so I'm pretty close to minus 0.04 and blah blah blah. Right, bunch of other stuff going on there as it goes. So I'm somewhere in that ballpark range, minus 0.04. So that is my absolute forward error. I guess I should put absolute forward error. The backwards error, and again this is in an absolute sense, at x equals 1 is going to be equal to, now I've got to use this expression. So again, this is the 0.5, 1 minus 1 squared over 2, because x equals 1. And I want the arc cosine of 0.5. The arc cosine of 0.5 is right about 1.04, blah, blah, blah. Right? It's a little bit bigger. I think it's about 1.4. Let me check on my computer here. It's 1.47 and some change. Whereas this one is 40 and then some stuff. Okay, so they're not the exact same number, but they're very close. And this is the difference between forward and backward. Don't expect them to be the same because they're not calculated the same way. But they are, or should be, in some sense, in the same ballpark. They could be a factor of 2, they could be a factor of 4. This will get into our sensitivity issue as it goes, but hopefully they should stay somewhat in the ballpark range. And so we've got that whole mess here, 1.047 and junk, and that's minus 1, right? Minus the x, and x was 1. So this is going to again give us something that's pretty darn close to, in this case we're positive, so it's 0.047 and stuff. But if you look at it, if we consider just in the taking the absolute values of these, magnitudes are fairly close. Gives us a nice way of getting an approximation. And you can see that I can at least get some idea of this. Now, not only are these the absolute forward and absolute backward errors, in this particular case, since I picked x equals 1, these are also the relative, because the relative error would then just be take these and divide them by the actual true value, which was 1, and dividing by 1 doesn't change anything. So that again makes it kind of nice for me. So this is an absolute forward or absolute backward just because I looked at x equals 1. If I had picked x equals 1/2 and I happened to end up with these numbers, when I divided by it, it would be multiplying by 2. As it goes, but I would have to take a look. In this case, I'd be dividing by y, which would be cosine of whatever that is. So in this case, so the backward error is a little bit nicer because I'm dividing by x. In this one, I'm dividing by y, which is the cosine of 1, and so that's 0.54. So this one actually is going to change a little, so it'd be divided by 0.54. So that'd be about twice. In any case, so we've got an idea of what we want for our problems, and we can take a look and find out forward and backward error. So what we'd like to do is check a condition number. Now this is why we developed forward and backward errors. The second reason, one, I mentioned, it turns out this one's kind of nice to be able to check problems because it will end up being computationally very good for us. In some cases that works, in which case it does, wonderful, we're happy to keep it. But what we're looking at, if you think, right, when we talked about the sensitivity issues, sensitivity was how much does the output change relative to the input? Well, that's change in y over change in x. And that gives you an idea of a slope, very true, and that's what we're looking for. But forward and backward error gives me those relative terms. Right? This is forward error is giving me an idea of how does the output change. Backward error is giving me a sense of how does the data change. So what we can do to measure our sensitivity is actually, we call this our conditioning, or the condition number, and we take a look at the change in the y, and we're going to do this as a relative value. Right, so our relative forward error, and we'll take the absolute value of it, divided by the relative backward errors. and take its absolute value. And that's how we're going to define our condition number. Now, if this condition number is really big, what that's telling me is the output is going to be much larger than what the input is. That's what it means for this. I mean, I don't care which one's the big one, which one's the small one in this case. It just says relatively this is bigger than that. This could be normal size and that could be minuscule. Or, you know, this could be huge and that could be normal size. I don't care, you know, how that works out. But the ratio between the two, if it's bigger than 1, that's telling you kind of the slope of that function f is much bigger than 1. That's going to be what we consider either a very sensitive or an ill-conditioned problem. This is ill-conditioned. You can also call that sensitive. Either way you want to consider it. Right? So ill-conditioned or sensitive. If it's, you know, pretty close to 1, then that means they're about the same. It means whatever your data inputs is, pretty darn close to your outputs. That's a nice condition. So we call that well-conditioned if the condition number is close to 1. It's close to 1, then we call that well-conditioned. Or we can also call that insensitive. So if it's, you know, insensitive or well-conditioned, our condition number is 1, which says the relative ratio of the relative forward error or the relative backward error is close to 1, and that's a good condition for us to be in. Now there's a lot of things, you know, people look at, they, you know, talk about amplification factors. I encourage you, read it over in the book. The big thing that I think is kind of helpful for you out of those is just this. He does give a good approximation formula. Some people get confused on where this one comes from. So what we consider is, in essence, our x hat, and I'm going to try to explain what I think is one of the more useful approximation formulas he gives you. Our x hat from the backward error you can kind of consider as being some x plus delta x. Right, some little perturbed value. That means your absolute forward error has to be equal to your f of the x hat, which is x plus delta x, and then that's minus f of x. Now, if you think about this one, if I took this whole expression here and I divided it by delta x, and I took the limit as delta x goes to 0, that would be, and this is pretty close to f prime at your point x, the derivative. But it wasn't divided by delta x. You can just multiply both sides by delta x. Now I've multiplied by 1, and therefore that gives me no room on my paper too, so I'll just put multiply by 1, delta x on this side. This is that multiplication by 1 trick. So now I find out that I can get an expression, you know, of my absolute forward error is pretty close to f prime times delta x. And then I can take that and divide it by f of x, and that gives me my relative forward error. So relative forward error is just going to be pretty close to f prime of x times delta x, all divided by your f of x. That's a good approximation. Now, to get the condition number, all I have to do, well, since this was my x prime that I said that is the one for my backward error, well, I therefore take this minus x, that just leaves me delta x, and I divide by the true, which is x. So my relative backward error is really easy to get to. And I told you this is sometimes the case if you pick things right. I just get that as an expression. So when I divide one by the other, right? This one divided by that, delta x is on the top of both, it cancels. And then this one will flip up because it's division, so I'll just end up with f prime of x times x over f of x, just by taking this one divided by that one. And that is equal to my condition number. And so you can look, in a sense, this is saying that your x times f prime is, in essence, kind of a sense of how well is your f. You know, and so you take that ratio and it gives you an idea of how that's scaling it. So, and if you look at Taylor's series, you get a very similar type of an expression off there. But it gives you a nice way of kind of approximating those. So it's a nice, fast way to do it. Some of the homework problems that are given from the book will allow you to do checks on this to see if you're able to get them. But these are kind of the big issues that I would like you to get from them. Some idea of the meaning of these terms. We've talked about quite a few of them here. I encourage you to go back. This is why I'm putting them on video, so you can go back and review them. The book should cover most of these. This is a fun approximation one. This is a basic definition, and the idea that it's kind of like a slope in a sense, I think is particularly important to understand, because it'll give you an intuitive feel. And that's what I would really like you to walk away with. So hopefully this will make a little sense to you. Go back and forth a bit, use the homeworks in the book to test it out, and we'll see you in class.